This is a help video for the Laplace Analysis Game in Circuit Tutor, Level 2, Problem Type 2. So we'll go ahead and go into that game. And of course we presume that you've already completed the introductory tutorial, which is available under the Impedance Simplification Game, which contains lots of very important information on how to do these exercises. Okay, so let's go ahead, and normally of course it would be highly desirable to look at some examples before you begin to do the problems. And assuming that you've done that, then I'm going to go ahead into the problem directly. Okay, so our problem here, we can see that it's a second order circuit due to the fact that we have both an inductor and a capacitor. It's a simple single loop circuit, but we do have an exponential type of source, which is a little bit different than we've had before in many of these exercises. So our first task will be to convert this from the time domain, where we have the henries and the farads and the time, into the Laplace domain, where we have only ohms for impedances and S instead of T. So starting off with the voltage source, that's 2e to the negative 10t u of t. So we may remember that the Laplace transform of an exponential function like that would be the 2 divided by simply the quantity s plus 10, where 10 is the rate constant in the exponential. Now if you didn't remember that, you can also pull up the Laplace transform table. That would be this entry here. Okay, now we'll convert the inductance, remembering that the inductive impedance is just SL. So here that's just going to be 2S ohms. And for the capacitor, we remember the impedance in the Laplace domain is 1 over SC, the quantity. So that would be 1 over the quantity 3S in this case. So that completes the conversion. The 2 ohm stays the same, and the name of the SOT variable has already been converted from the time domain lowercase function of time to an uppercase function of s. So now we'll go ahead and check that. And that is correct. So now we'll wait for it to replot here in the Laplace domain. And then we'll start our analysis. So we could possibly combine these two elements, but we don't really need to do that. We can just treat this as a simple voltage divider, since that'll our formulas that are available will accommodate up to 3 elements in series. So I'm just going to go ahead and solve this directly using single loop analysis. In other words, that will allow me to do voltage division. And then in this case, really the only option would be to select the SOT branch voltage to enter that. So that's V naught bar or bold, and that's going to be equal to, and now we're going to use the voltage divider formula when you have 3 impedances. Looks like this. So first of all, we have to put in the source value, which is the 2 over s plus 10. So I'll enter that here, 2 over quantity s plus 10, and of course we have to use parentheses to put the entire expression in the denominator. And then we should also always check polarity, very, very important. So we check here that the positive side of this source is in fact connected to the positive side of the SOT voltage, and the negative side here goes to the negative side. That means that this will have the same polarity as this, or alternatively you can think of it as the current is going to go from the positive side of the source clockwise here into the negative side through the passive elements, which means it'll be going into the positive side of this voltage, therefore giving us passive sign convention, hence the positive sign here. Okay, and then the numerator in a voltage divider formula is always the impedance of interest. So that's going to be the 1 over quantity 3s. And again, we can use square brackets or parentheses to enclose the denominator, but we for sure don't want to write 1/3s because that would be 1/3 times s, which is not what we want. So we'll copy that also here, just to go into the denominator as the first impedance. We need to sum all the impedances in the denominator. And then we'll have the 2 and the 2s from the inductor, these 2 impedances. And remember that the voltage divided by the sum of those impedances is really just the current that's going clockwise in the circuit. So naturally, we multiply that current by the impedance of interest to get the voltage of interest. That's a way you can check that this formula actually makes sense. Okay, so we'll go ahead and check that. And having done that now, we just need to put in a final simplified form for this. So we'll click no more equations since we've entered all the equations that we need. And it will alert us now that because we're going to be doing an inverse Laplace transform in the next step, or the partial fractions expansion for that in the next step, that means that we're going to need to factor any quadratic terms that appear in here. And there will be quadratic terms because it's a second order circuit, and we can see that kind of from the form of this. So we'll keep that in mind. And so I've done that here on paper. So I've written out the expression that we had, the 2 over s plus 10. I've dropped the units here because we know this is volts, which is going to match this, and the ohms are going to cancel out. So I've just left those out here. And we have 1 over the quantity 3s divided by 1 over the quantity 3s plus 2s. So now, in order to simplify this, we never want to have fractions inside fractions. We want to rationalize that, and to do that, we multiply by the common denominator that's present in both numerator and denominator. And if there was other terms here in the denominator, we would find that the total common denominator and multiply top and bottom by that. But in this case, it's just the 3s. So we'll multiply the top by 3s and the bottom by 3s. So we're multiplying by 1, which of course is legitimate. That makes the top just become 1 here, and that just leaves us the 2. Then we'll still have the s plus 10 factor. And then here, when we multiply through by the 3s, this term will give us then 6s squared, which is written here. And then the 2 term times 3s will give us 6s, which is written here. And then this term, of course, times 3s just gives us 1, so that's the last term. So I've written this in descending powers of s as required when I put this into Circuit Tutor, and just also the normal way to write a polynomial. Okay, now since I'm going to do a partial fraction expansion here, well, at this point really just put this into factored form, it makes it a little bit easier if I rationalize this, if I set the coefficient of the highest power of s here to be 1. So I'm going to divide both the top and the bottom by 6. So 2 divided by 6, of course, is 1/3, or 0.3333. And then down here, s plus 10 stays the same, and we have this divided by 6 is s squared. The 6s divided by 6 is just s, and the 1 divided by 6 is just 1/6, or 0.1667 in decimal form. Okay, so that's our rationalized form, and now we need to factor the quadratic term, as I mentioned before. So we'll use the standard form of the quadratic formula that I recommend, which is if we have ax squared plus bx plus c equals 0, then the roots are going to be written as x equals to negative b over 2a plus or minus that same quantity squared minus c over a. This form is generally advantageous over the form that they taught you in high school, but it's very similar. Okay, so now we'll just plug in the coefficients here. So our a is 1 and our b is 1 also, so we just have the negative 1/2 here. And then plus or minus the square root of that same thing squared, minus the c over a, which is just the c constant here, the 0.1667. And now we can go ahead and evaluate that on a calculator, and it turns out this discriminant, as you can probably see, is going to be 0.25 minus this is going to be positive. So therefore, we'll get real numbers, and they're going to be negative, real, and distinct, as we'd expect for a stable circuit, which this really has to be. So those values on a calculator evaluate to minus 0.2113 and minus 0.7887, and those units would be inverse seconds, because remember, this is a complex frequency, which means it's per unit time. Okay, so now we can rewrite this form for V naught as the 1/3 here on the top divided by the s plus 10, and then we're going to factor this term. So we now have to have s plus this value as a factor and s plus this value as the second factor. Remember that if we put minus signs in here and then put in the negative values, that would not give us 0, which is supposed to do since these are roots. So we have to have the plus sign there, as always in algebra. Okay, so now we have our factored form, so we can go ahead and enter that into Circuit Tutor. And just to show you, I can enter a fraction, so I'll just type 1/3 there. It'll convert it to decimal for me. divided by, then I'll need a square bracket to enclose the entire denominator, since there's multiple terms that multiply each other. I can't use parentheses or on parentheses, however. So I'll put a parenthesis s plus 10, close parenthesis, and then open another, s plus 0.2113, close that, and open another. And then we have s plus 0.7887, close that parenthesis, and then finally close the square bracket to differentiate the entire denominator there, basically, or identify it. Okay, so now we'll go ahead and check that expression. And you see it converted the top to just 0.333 and 3 in decimal form. That is correct. And now, as it tells us, the next step is to carry out a partial fraction expansion. And so we'll go ahead and do that. And we just have one SOT variable to do that for, so I'll select the partial fraction expansion menu. And so now we'll have the V0 of s is what we're after. And again, we're not going into the time domain yet. We're going to do partial fractions first and then enter each step at a time so we can check our intermediate results. Okay, so since we have 3 poles here, that is these 3 terms in the denominator, that means we're going to need 3 terms here for the partial fraction expansion. And these are all going to have units of volts because we're looking for SOT voltage, so I'll just change the amp volt watt selector to that, as we need to do. And then I've gone ahead and done the partial fraction on paper here. So we'll set this equal to a over the first factor, s plus 10, b over the second one, the s plus 0.2113, and then c, I'll call it here, divided by the third factor, like that. Now, to compute a, b, and c, the easiest method there, we don't need to cross multiply or anything like they sometimes teach in math class. We'll instead use the Heaviside or method of residues, meaning that for a, I'm simply going to multiply through by this denominator, the s plus 10, and that will give us a factor of that here and here. And then we set s equal to negative 10, which basically makes those factors go to 0, wipes out the b and c term very conveniently, and just leaves us with a. And then on the left-hand side, when I multiply by the s plus 10, of course, that just cancels out. And now we set the s equal to the negative 10 in the remaining terms. So we have the a is equal to the numerator divided by just this term with negative 10 substituted for s, and the same thing for this term, making the same substitution. Now we just do the arithmetic there on a calculator and find that works out to 0.003697. Now do be careful, just because these are small numbers doesn't mean that you should round them excessively. You always want to keep it probably at least 3 digits to meet the error criteria, and I've kept 4 just to be on the safe side here. But don't round off to a certain number of decimals after the decimal point. That's not meaningful. What's meaningful is the number of significant digits, right, which doesn't depend on where the decimal point is located. Okay, then for b, we multiply by s plus 0.2113, and that gives us that term here and here, and then we set s equal to minus that value, which will wipe out this, making it equal to 0, and it cancels this term here. And so then b will just be equal to this numerator divided by the s plus 10 with the s now equal to minus 0.2113. And then this last term here, again, this term's gone, so we have the last term minus 0.2113 plus 0.7887. And once again, just doing the arithmetic there on a calculator, that works out to 0.05898. And then we do a very similar thing for c here. Multiply through by this denominator and set s equal to the negative of that value. And that gets rid of these terms and then cancels here. So now we have the 0.3333 divided by, again, now it's going to be the minus 0.7887 plus 10, and same thing in here. And then this term's gone. So then we just, again, evaluate that. This time it's negative 0.06268. So we've completed that, and now we know what to enter here. So we'll just go and put in the numerator. That's going to be the 0.003697. And then the denominator there is the s plus 10. And then for the b term, that's going to be that value of 0.05898. And I could round that to 3 digits, certainly. Don't round it too much, though. You may miss the error criterion if you go down to, say, 1 or 2 digits. Very likely you will. So that's going to be the s plus 0.2113. And then here, again, just the last constant. Oh, that's a -1, so I'll put a minus sign out front. And so that's 0.06268 divided by the s plus the 0.7887. Okay, so I'll just proofread that very quickly here. That looks like that is correct, I believe. So we'll go ahead and check that. Okay, so that was correct, and now we've entered all the partial fraction expansions we need to, so we click no more equations. And it tells us the next step is going to be to do the inverse Laplace transformation to go back to the time domain. So now we're in that mode, and we can select this. And it reminds us that there is an extra palette here if you need that, if you can't find the terms you need in this one. But in this case, we have everything we need here. So our v0 of t is our variable, and then that's going to be equal to, and then each of these terms, they're all of the form, well, a constant over s plus a, if you will, and therefore they all will have the same inverse transform, which is this decaying exponential. And however, I do need a bracket there, so I'll stick a bracket in front so that I can multiply all of them by u of t, because everything has to be multiplied by u of t basically in the time domain when we do Laplace. So here, that's going to be a volt, put in the unit, and we've got our u of t, and all of these exponentials are decaying, so I'm going to make sure those are all minus signs, otherwise they would blow up, and that wouldn't be good at all, because then the circuit could literally blow up too. And our time constants here, well, I'll put in the constant first, I guess, so that's the 0.003697. And then our time constant now, we have to take the reciprocal of the 10 inverse seconds for the first one, since that's the rate constant, 10. And so that gives us 0.1. And then put in the second constant there, 5898. And again, negative exponent, but the time constant now is the reciprocal of the 0.2113 inverse seconds, which is 4.732. I'll just put 4.73, I guess. And then we enter our third coefficient. Well, again, this one minus, so I'll put in 0.06268. And then the reciprocal of that rate constant was going to be 1.27, let's say, seconds. And then we can just very quickly check that to make sure I didn't make any typos. And it does look correct. So I'm going to go ahead and check that. And that is correct. It's been printed on the screen. And now we just have to hit no more equations, basically, to complete the problem. It will go ahead and give us a PDF transcript of all the steps that we took to solve the problem, which was not terribly long here. And then you can always access that for studying or review from the review work on the level manual. And you do have the option to view a detailed explanation. I think in this case it's not going to show us a lot that we need. So, but if you want to review, you can always do that. I'm just going to skip that step here. And then again, here's the review work button. So that completes this example.